So, electricity production. If we're going to make any progress, we've got to do it without CO2 emission. I just want to show you a few little slides that tell you about that. And this is the amount of CO2 that's emitted per kilowatt hour in grams of CO2. And here you see for wind and for nuclear, it's essentially nothing. So you're winning. These are full life cycle calculations, both for the building but also for the fueling of the plants. And here you see gas, here with a normal carbon combined cycle gas turbine system, and here coal. If you did nothing about the CO2, if you do something about CO2, you put in carbon capture and sequestration. That means capturing the carbon dioxide and usually pumping it down underground and pushing it down there for the foreseeable geological future. And if you do that, you have to have this capture system which will bring down the amounts of CO2 emissions in the operating phases. Unfortunately, we don't have, and I'll repeat this again in a few moments, we don't have a real proven technology for this carbon capture and sequestration. So that's a technical challenge. There's one prototype system in Canada that is starting to work, but that's the only one. And remember the thing to remember is 40,000 million tons of carbon dioxide have got to be trapped, captured, and pumped down underground. So there you have it. You're not going to be able to use fossil fuels without this carbon capture and meet those emission levels. And that means coping with this 40,000 million tons of CO2 emissions per year. That's going to need a lot of R&D. It's not beyond the wit of man and woman to come up with schemes to do a proportion of that at least, if not all of it. But you've got to do the research and the development, so there's lots of very good engineering and technical research and development to be done to be able to move us forward. Now how about, so that's the CO2, what you have to do. How about the economics of these things? We will argue, or one can argue forever about the costs of electricity. I'm just taking this from the Department of Energy and Climate Change in Britain, comparison for Britain for different sources of electricity. Now, you have to remember that again, this will be different for different countries, wherever you are in the world. But numbers will not change a lot from one place to another, but they will individually be different. If you're living somewhere very, very sunny with large desert area, then clearly you're going to get a lot of sun and you're going to be able to make a lot of electricity from solar power. And the more deployment you have of it, the cheaper it gets. So it's clearly going to be beneficial in different ways in different parts of the world. And here you see the large-scale solar photovoltaics. Here, offshore wind, and note, these are not cheap. They're hard to do. Now, that's the position. I tend to look at this and say, well, they're all going to be somewhere between 80 and 100 in this time pounds per megawatt hour. And don't ask me which year that was, because I think it was about 2012, so we're already out of date with that. But they were all produced in the same year. But what I want to do want to point out to you is this issue of backup and intermittency. And here you see the system costs. This is the costs of the electricity grid that you have to move electricity around from your power stations to your user, your consumer, wherever they are. And you notice down here two things. First of all, nuclear, coal and gas, the grid cost is really quite small. That's because they can put out power at a very easy rate. at a steady rate. They are very easy systems in that sense to operate. Whereas with offshore wind and onshore wind and solar, you get an enormous jump in the costs of the grid system, because you've either got to put in backups or you've got to have very, very clever grid systems over the countries wherever you are to be able to move the electricity around from where it's generated to where it can be. And you have to worry, for instance, if it's solar, what happens during the night time, and for the wind, we have to worry about what happens when the wind doesn't blow. And these are extra costs that usually people, when they do these comparisons, don't ever tell you about. They just tell you about the cost of a propeller putting up in the air a turbine to get you wind power, or a solar panel. They don't tell you about the grid costs that have to go along with it. So, I'm going to take the UK, because I know a lot about that, as a bit of an example. And I'm going to show you what we were going to do in Britain. And here is a plot of the gigawatts of electricity that we have. And remember, technically, if we're going to solve the CO2 problem, we're going to require more and more gigawatts of electricity. Here you see how it was constructed in the year 2015. A little bit from renewables, from nuclear, mainly from gas, because we have gas from the North Sea and from Europe, coal, and then these other small parts. Note this interconnector capacity. That's because we have a cable that runs from England to France, and we can move electricity backwards and forwards on that cable underneath the channel which separates the two countries. And I can tell you that at the moment in Britain, that interconnector is usually running at full capacity, taking nuclear generated electricity from France into England. And that's a vital ingredient to us being able to supply, give ourselves enough energy, because here is the demand line. Now, what happens as we go into the future? In the future, we hit a problem here where demand starts to exceed installed capacity in about 2023, 24. Notice we're being very good. We're turning off all of the coal-fired power stations, so we're cutting down on CO2 emissions to a large degree, and we're introducing, keeping these here and increasing the renewables somewhat. How are we in Britain going to deal with that? The way we were going to deal with it in Britain is that we were going to have a big new build of nuclear power stations starting back down here in 2012 or so, to be able to bring them online to cope with that problem when we had the gap in 2023, 24. That was the solution, was to build new nuclear power plants. That was the British strategy to deal with it. And it still is the strategy. And it's a strategy that's being used, was conceived to work all over the world. Here you see the increase in power stations going from now until 2030, where a lot of these new nuclear power stations were being built, particularly in China, the rest of Asia and India. They were going to be the main builders, whereas Europe, the USA, they were almost staying constant. In Europe we were staying constant, in Britain we were staying constant because we were taking 50-year-old reactors off the grid because they'd come to the end of their lifetime, and we were putting new ones in place. We weren't increasing the number of reactors, perhaps their capacity we were increasing. Now, you look at that and you see that this is what the plans were, but those plans were still the plans that actually didn't reduce the amount of percentage of fossil fuels that we were using. So actually, if we're going to use nuclear to build this, we've got to build even more reactors than are shown in here. And that's one of the things that's the big issues for us to deal with. Now, there's a problem, however, with that, because there's a limit to the amount of uranium that we can mine, or we believe there is. Here you can see that plan of what are called light water reactors, because they were all light water reactors, was consuming uranium as we're going up to 2060. And here's the cumulative natural uranium use, and these, on these lines, this blue line, and these were the resources we believe we had. So somewhere here, perhaps even sooner, in 2060, would exceed the amount of uranium we think we had on the planet. So that wouldn't be a viable solution. You have to find some other way of getting power out of the nucleus.